All right, so let's begin this talk of today. So we're happy to have Michael Sperling. We'll talk about magnetic quivers. Please.
Thank you very much. Okay. Thank you everyone for being here. Thank you to the organizers for organizing this very nice event. Last time I was actually in Trieste is when I was a PhD student, so that's unfortunately a while back. But today I'm going to use the hour to tell you about, first of all, magnetic quivers, quantum branches, and Chern-Simons matter theories. And that's also kind of the order of how the talk proceeds. So I introduce the magnetic quivers as a solution to a problem that is related to what I call the quantum branches. And then once I've advertised this enough and convinced you that this is something nice and doable, then we're going to see how we can apply this to some other class of theories, which are called the Chern-Simons matter theories. Okay. And the talk is based on the works I had together with Fabio and Sinan, who are conveniently sitting in the back. So if you should have any questions, you can reach out to them after this talk. So let's get started with the motivation. So what is the sort of the general framework? Well, the conference title basically does it very nicely: Quivers, Symmetries, and SCFTs. So here I take the point of view that we have supersymmetric, superconformal theories that are sort of expanding our understanding of quantum field theories in the sense that we have high-dimensional theories, strongly coupled theories, non-Lagrangian theories. And one very nice way of constructing many of these examples is that we use some kind of string theory constructions, which can either be you have string F and M theory on a singularity, you have brane constructions, or you have mixtures thereof. Right? So that's a very well-established tool set. And with this kind of tools, various people have been doing a lot of amazing work. And by now we have a very vast zoo of theories with different types of supersymmetry. Right? So you can pick your amount of supersymmetry that you like, and then you can go ahead. Here, what I like is, Here what I like is that we have, or I focus on theories with 8 supercharges, right? So 8 supercharges for the n equals 2, as we, for instance, heard with Antoine, is a very nice playground because that's enough supersymmetry to have exact computations, but still low enough amount of supersymmetry to be non-trivial, right? So if we now have this nice construction principle of having these beautiful theories which tell us something about quantum field theory, but also we know there's the zoo of theories, you might ask yourself, okay, can we do anything to bring some kind of systematics into this game? And ideally, if you want to study quantum field theory, you would say, okay, I study the local operators, I study correlation functions, and then I'm very, very happy with this. But you can convince yourself by talking to various people in the audience that this is usually very hard. Right? So what we want to do is we want to take a step back. We want to focus on something that is simple, computable, and quite a robust quantity to compute. And once we take these quantities, we hope that this information is enough to distinguish different theories. Right? So that's kind of the hope or the aim of the game. And the kind of quantity list that I like, or that you can also look at, is symmetries, vacua ground state, and partition functions. And particularly for me is I like to focus on these vacua, and one type of vacua that's called the Higgs branch. So since this is a larger audience and I don't quite know what everybody's working on, I'll take the liberty to just briefly go on the Higgs branch, tell you a little bit about it, and then tell you why this is a problem. Okay. So first point, if you take this picture here, you may see words and ask yourself, what is the setup? So the setup, take an example for the n equals 2. Take a Lagrangian theory, then you know this kind of theories you can construct from supermultiplets. You take hypermultiplets, vector multiplets. Due to the amount of supersymmetry, they have scalar fields. If you want to have a supersymmetric solution, you need to find a configuration of the scalar field such that the scalar potential is 0. Right? So that's sort of the solution space to everything that I drew here. That's the supersymmetric ground states. Now, they then distinguish into different branches depending on what kind of scalar fields are non-trivial and what kind of resulting physics is in such kind of vacua. Right, so one particularly interesting branch for me is the Higgs branch, where only the hypermultiplet scalar fields are non-vanishing and the vector multiplet scalars are trivial. Right, and that's called the Higgs branch because you do fundamental Higgsing, basically. On the other hand, there's the Coulomb branch, the one Antoine mentioned. Here we sort of would do a joint Higgsing, so we always have U1 gauge fields in the IR, so we have some Coulomb interaction, hence the name. What I like is that this Higgs branch has a very nice geometric structure in this Lagrangian setup. it is what's called hyper-Kähler or symplectic singularity, as Antoine has mentioned. And then Lagrangian setup is a very nice and geometric description. You start from the space of hypermultiplets. You see it's a flat hyper-Kähler space. Then there's a gauge correction on it, which is compatible. And then you do the condition of supersymmetric ground state and identifying gauge equivalent solutions, and you find what's called the hyper-Kähler quotient. Right? So that's a very nice, clean way of getting what is the Higgs bunch. And by non-renormalization theories, that's very nice and easy. That's the answer. But if you remember the slide that I told you before, we have theories which are non-Lagrangian, highly strongly coupled, or high-dimensional. For those ones, we don't have this luxury. We still know that the Higgs bunch is a hyper-Kähler space because the amount of supersymmetry is the same. We have still this SC2R symmetry, which is the hyper-Kähler rotations, but we don't have this luxury of constructing it explicitly from some Lagrangian, right? So that's the thing, that the Higgs bunch is there. It has in all of these dimensions, 3, 4, 5, 6, it has the same geometric type, but we usually don't really have an understanding of what it is in the full quantum theory. That's why I'm interested in them. Now you might ask, why do you care about the Higgs bunch in particular? What do you learn from this Higgs bunch? Well, there's a bunch of information that is hidden in this space, right? So we have isometries of a geometric space. There is one type of global symmetries, that's the flavor symmetries. Right? That's a very nice feature. We have singularities on it. So here we know if you go to certain loci, we get extra massive states that you can study from the Higgs bunch, or you look at its stratified structure, and then you get basically Higgs mechanism information. Good. So now the answer and the question. Once we appreciate or once we like that these Higgs bunch is actually quite a robust and universal feature that we can study in supersymmetric theories from 3 to 6 dimensions with 8 supercharges, and we know that they're sort of beyond the standard Lagrangian construction, you ask how do you study them? And the answer is the magnetic quiver. Okay. Now, what is that? The magnetic quiver is using the feature that there's another type of modular space in supersymmetric theories which has the same geometric type. And that is the 3D Engels Coulomb branch. And that one is hyper-Kähler or symplectic singularity. But here we already know it's very, very different from the classical Lagrangian description because that one is always a quantum corrected thing. Right? So it's always a different class or a different realization of the same geometric type. That's why it was first difficult, but now it's sort of a nice way of turning it around. We're using this different construction to study these Higgs bunches that we don't really understand. Okay. The idea is that you have this Higgs bunch here that you want to study. And the proposal is, okay, since it's not a classical hyper-Kähler quotient, it could be a Coulomb branch, right? Because a Coulomb branch is a different hyper-Kähler construction or symplectic singularity. And say, if I can find an auxiliary theory, which I call Q, such that a Coulomb branch is that Higgs bunch in question, then I'm very, very happy because now I have a way of going ahead. And this Q we call the magnetic quiver for reasons that will become clear in a minute. Yes?
The problem below 4 dimensions of the healers. Why are you focusing on 4 above?
3 dimensions, it's, well, if you go for the Lagrangian theories, it's fine. You could have, yes. Yes, that's true, that's true. Yes, that is correct. I have not reached 3 yet. Well, actually, I could go to 3 because that's the 2/3 of the talk. Okay. Right, so we go certainly to 3, and then we see that there's also a problem. Okay, so as Andres pointed out, this one goes to 3 to 6, not just 4 to 6. Okay. So the idea is this: if this exists, we have this, and we have something to describe this universal feature. Now you ask, okay, how do you do this, or is there any way of accessing this magnetic quiver or this auxiliary thing? And there are various ways of doing it. Some more systematic than others. The first one, and sort of the one that is, let's say, the cleanest or the most intuitive, is you come from brane systems in type 2. One example that I would like very much is if you focus on this example of the small 8 instantons. So you would have an M5 going into M9. You would have a corresponding type 2A brane setup where you have the 8 branes, just the lines. You have an orientifold that's theta coming from the M9. You have the NS from the M5. And then you have some D6 branes. Long story short, you have a brane system, and I can massage it around. I can massage it into this. Sorry, wrong button. I can massage it into this in this configuration, and then from this configuration, I give you some rules that tell you should read off this quiver. You should read off this quiver, and now you take this quiver as an input for here. But actually, you don't need to do a lot of computations just now, because you can look at this quiver very hard and realize it's not just a random quiver, but it's actually the the affine Dinkin diagram. Right? So there it is already giving you a hint that something with the 8 is actually the right answer here. And if you sit down and do the computation, you find it's really the 1E8 instanton modular space. Okay, good. So that's brane system. So you have a nice way of, from a brane system, reading off a quiver, provided I give you some rules how to do that. Then there's another method. Let's say it's indirect in the sense, if you know enough about the Higgs bunch in question, you can many times construct examples or can sort of constrain what is the type of magnetic quiver it should be, and then check whether it gets works by checking global symmetries, dimensions, Higgs mechanisms. Right, so that's a nice way that has, for instance, worked in some works by Antoine and Julius on the 4D NX2 theories. Another thing that should work, and somehow, to my understanding at least, doesn't really work yet, is if you have dual realizations of the same thing by, say, M or F theory on singularities, then there is a statement that the corresponding Higgs bunch should be coming from the complex structure deformations of that singularity. So it reasons, or it stands to reason how this works in more detail, right? So that's a claim that you hear sometimes, but I don't really know how that works. So if anybody knows how to derive it, that would be very, very nice. Because in principle, it should work somehow, but I haven't seen a way of doing it generically. Good. So given that we have a magnetic quiver, or I give you this graph, what can you actually compute? Well, you can compute various things depending on how much time you want to invest. You can compute very fast dimensions. You can more or less read off from the graph what are symmetries. And then if you sit down and do some more computations, you can get operator spectra and this stratification. Now comes an advertising slide, just to tell you that magnetic quivers have been applied in a variety of different setups by a large number of people in this audience. So if you see something that you like, you can just reach out to the persons that I've cited here. And what I want to convey with this message is that it's a nice unifying framework to a large class of theories across dimensions that works for these quantum Higgs bunches. Right? And if you just use the magnetic quiver, you have already access to a lot of information. And one thing that I wanted to emphasize on the next slide is that there's also a very natural way of connecting it to the Higgs mechanisms or the RG flows. But for this, let me just go back, since I don't quite know what everybody's doing, at least for some people. What is a magnetic quiver and what do I mean? So by magnetic quiver, I really just mean I have a graph that is based on some Cartan matrix adjacency matrix, and then I assign to it what I mean by the supersymmetric quantum field theory. So that means I give a meaning to what I mean by the vertices and what I mean by the edges. And it's, in the most cases, it's a very vanilla setup. You have some vector multiplicator, you have some bifundamental matter, and then you're ready to compute. And magnetic really just means it's the 3D anchors for Coulomb bunch that I want. Right, so that's the basics of this. What we also need to know a little bit is how this 3D anchors for Coulomb bunch actually becomes the more interesting or sort of more useful way of constructing these symplectic singularities. The reason is that we sort of need to use a different set of coordinates to describe it, and that's what's called the monopole operators. And here, the only thing that we really need to know is that we have a nice way of labeling them by the weight letters of the dual group, and we know the R charges and the global symmetry charges. Once we know them, we are ready to sort of do counting arguments. Okay, and what we then need to know is, not too much in detail, but just for computational reasons, is one very powerful way that we have been using a lot is this Hilbert series. So that counts all these monopole operators up to dressing. And the very nice feature is for 3D n equals 4, the monopole operators are gauge invariant. They don't carry any gauge charges. So this formula really simplifies down to just the sum. And then you count monopole operators according to their charges and up to their dressing factors, right? So that's basically, you have a monopole background, you put in what are the residual theories, and then you can compute this sum. And it's really important that it's a sum. Good. Now, we can go back to the question, how do we relate this now to Higgsing? That was one of the points that I wanted to advertise, and that is sort of the last introductory slide that I want to show. So here the question really is, suppose we have a magnetic quiver for a theory T, and I say it describes this Higgs bunch by the Coulomb bunch. But then you can also say, okay, Higgs bunch usually is connected to Higgs mechanism, right? So I want to know what happens if I Higgs or RG flow my theory T to T prime. How is this reflected in the magnetic quiver? Or different question, what is the magnetic quiver of T prime? If you just live in 3 dimensions, you can also ask the same question, what are the Coulomb branch Higgsings of this 3D n equals 4 auxiliary theory? And the answer that we have provided with Antoine and Zhenghao is that we really just use the quiver as a graph. So we just encode the information in its adjacency or shape matrix and the rank vector. And then we said we found or proposed that the 2 elementary Coulomb branch Higgsings that can happen in this class of theories that we're looking at is decay. That means the shape remains and the rank vector decreases in a way that the result is still a good theory. And the second one that can happen is fission. That means the shape remains again, but the rank vector now splits in a way that the resulting theories are good. Right? Whatever I mean by good, but just a well-defined theory. And once you employ these 2 basic options, you can basically go through the whole Higgsing tree, and you find what happens with the magnetic quivers. To advertise this, you can take your favorite theory, which has a brane description, or just you know the magnetic quiver. So for instance, you take something that lives in 6 dimensions, is something like this. It's again a theory that you can realize via branes. We know the magnetic quivers due to various reasons. And then the only thing that I need to show you is that this is the starting magnetic quiver. Then you unleash what you know from decay fission, and you get this diagram. This diagram is, if you just think about the magnetic quiver, the Coulomb branch Higgsing of that 3D theory. That's what it is for now. And then we can translate it back into what happens on the 6-dimensional side. And for this, of course, it's very helpful that we know where the theory comes from and how we constructed it. So by knowing that we constructed it, for instance, from a brane system, we can then translate it back into, how big is this actually? Into a Higgsing tree or Higgsing pattern of the 6-dimensional theory, right? And the thing that I just wanted to highlight is that I have black and red transitions. Black is what I call decay, red is what I call fission, and they can be related to what is known in the 6D literature. So we, for instance, have this nilpotent Higgsings, but we very clearly see just by using this logic that in 6D there's actually more than just nilpotent Higgsings. So you really need to take fission into account. Okay. So that was the introductory slide of there's a problem and there's a solution. The problem is, well, not a problem. The feature is that Higgs branches are actually a very nice and universal quantity that you can study of theories with 8 supercharges across dimensions, and it fits into the scheme. We want something that is robust, computable to some extent, and it's useful for a large class of theories, right? And the magnetic quiver is the answer because we have now a lot of machinery from the 3D n equals 4 background. What I now want to do is I want to use all of this advertisement and tools that we have developed to a different set of theories which have a similar problem. And those are precisely these Chern-Simons matter theories in 3 dimensions. Any questions up to here? Okay, good. Then let's go to the 3D highly supersymmetric Chern-Simons theories. So what is the starting point? I want to construct them to be highly supersymmetric. So I start again from an n equals 4 setup. I take the vector, the hypermultiplet, I decompose them as n equals 2. I join them with the superpotential, which makes them n equals 4. Very good. Nothing happened so far. Now we add the Chern-Simons term. We do so by doing the usual Chern-Simons term plus a superpotential term. And then you can ask yourself, what happens if I add these terms? How much supersymmetry is left? And generically, the answer is n equals 3. But then we also know that highly supersymmetric Chern-Simons theories are possible if you have special combinations of matter and Chern-Simons levels, right? So that's a thing. And then we know if it's an n equals 4 Chern-Simons matter theory, then we know as an SCFT, it has again the same features as a 3D n equals 4 non-Chern-Simons theory. We have 2 R symmetry factors. Those are basically hyper-Kähler rotations on 2 maximal branches. Whereas if you go to the n equals 3 case, we only have 1 single SU2R factor. That one is basically the diagonal one of the origin of n equals 4. And we have many, many maximal branches. But since we have an SU2R, they're all of the same geometric type. They're still hyper-Kähler, they're still symplectic singularities. So that's already a good thing. Now, there's a problem now if you go to Chern-Simons theories, because now the monopole operators pick up gauge charges. Right, so the argument that we did on the standard Coulomb branch that the monopole operator is gauge invariant and already defines a good chiral operator is not quite true yet. We need actually charged matter fields to make gauge invariant combinations out of these objects. And then the answer is basically, or the question you can ask, since I know there's maximal branches and I know that monopole operators need to be addressed, how would you count, for instance, monopole operators on a certain maximal branch? And we can be, well, we are very happy that there is in principle an answer that is due to Noppadol and collaborators that is in principle the same as the monopole formula. But there's two subtle differences which make your life a mess. The first one is that the monopole operator carries gauge charge, so you need to take the gauge charge into account. Then you need to compute the residue theory in the monopole background, and then you need to do this gauge integration over the residue theory. Right? So there's already an additional extra step coming up. You need to do an integration. And then you need to do the sum. Right? So in principle, the way of approaching the maximal branches is clear, but it's just a lot harder than on the non-Chern-Simons 3 lengths for Coulomb branch. Right? So that was the sort of the motivation on why we thought it might be useful and interesting to approach the maximal branches of the Chern-Simons matter theories from the magnetic quiver point of view. Because this is a computationally, in principle, possible way of doing it, but it's very hard. Right? So let's try to see whether we can do a simpler way of doing it. And by doing so, or one way of doing it is basically we go back to the stage where we know how to do things, and that is a brane system. Right? So as in the magnetic quivers, the nicest way of doing things is you go back to a brane system. Here, the realization is you take your 5 branes, NS, D5, you can take 1, kappa, you can take PQ5 branes, take them and build a Chern-Simons matter theory out of them. That is, for instance, realized by a brane configuration like this, where I say you have NS branes, like the red ones, you have D5 branes, and then you have this sort of PQ5 branes, which are sort of drawn diagonally. And the Chern-Simons theory is then realized on the world volume of these D3 branes, which are the black solid line. Now, in these brane systems, we have a very nice and intuitive way of reading of the maximal branches. Right, so what is a moduli in a brane system? A moduli would be you have a D3 brane that can move between the same type of 5 brane in the direction along this 5 branes. Right, so if I take for instance, the NS 5 branes as an example, I can move D3 branes along this direction. Right, this would be one modulus along the NS5 branes. If I take a D3 brane and I can move it along this 1, kappa 1, 5 branes, that's another type of modulus that I can turn on. And now the question is, can I use the brane system to cook up a recipe that gives me magnetic quivers for each of these maximal branches? Right? And the maximal branches are really how many different types of 5 branes do you have in your game, and how many D3 branes can move between these particular 5 branes. And then translate this into magnetic quiver and verify that what you do is actually correct. Right? So that's the idea. Sorry. So let's go back to the non-Chern-Simons setup. What do we know? We know there's 2 types of 5 branes, NS5 and D5. We know the D3 moving between the NS, that is the Coulomb branch moduli. We know D3 moving between the D5, that's the Higgs branch moduli, right? And here we have a very nice setup. We know these 2 branches are separated by the R-symmetry, and we know they are separated by the type of operators. The Higgs branch is a very nice classical thing as the meson operators. The Coulomb branch is the monopole operators. Good. Let's go to Chern-Simons and just take 2 5 branes. So when we have only 2 5 branes, then we have an n=4 Chern-Simons matter. And you can play the same game. It's the analogous thing. You take D3 between NS5. That is now one maximal branch. Let's call it A branch in order not to confuse ourselves. And the other one is D3 moving between the 1, kappa. And let's call it the B branch. But still, there are 2 maximal branches. We have by n=4 in the IR. They are separated by the R-symmetry. But both of them are composed by monopole operators. Right? Both of them are composed by monopole operators which need to be charged by matter field. Right? So they're not really separated by the type of operators anymore. Hence, both of them become actually quantum branches. Right? So in the non-Chern-Simons setup, you could argue the Higgs branch is not a quantum branch because you have non-renormalization theory, it's just mesonic operators. The Coulomb branch is always a quantum branch because you need to work with monopole operators. If you go to Chern-Simons, both of them are composed by monopole operators, so in both of them you have the same mass, and you need to find a way around. Right? Good. And you can, of course, in terms of branes, there's no difference between 2 types of 5 branes or many 5 branes. It's the same exercise. The only thing that now different that the maximal branches are not separated by their R-symmetry anymore. But otherwise, there's no difference. Okay. So how do we do, or how do we proceed now in order to capture these quantum bunches is, again, the answer is magnetic quivers, and that's sort of what we do now. Okay. So 3D Anchors 4, you see, this is based on a work that I had with Fabio in the beginning of the year, just so you have a picture and you can ask questions for later. So let's go for an example. Let's go for the simplest example. We're going to be very generous, and we start with the simplest non-trivial Chern-Simons level, that's 1. In this setup, we have NS branes, so the red ones, and we have 1,1 branes. But here, actually, there's not much to do. We know for a while already that there is an SL2Z duality that takes you from a Chern-Simons theory to a non-Chern-Simons theory. Right, so if you do this, you get basically this brane setup. So what you do is the NS branes remain invariant, and the 1,1 become the 5 branes. And then you would read off a 3D Anchors 4 non-Chern-Simons quiver like this, and then you can say, okay, since I already know everything about 3D Anchors 4, I'm happy, I don't need to do anything. But the example is still instructive because you can appreciate the following sort of huge figure. So on the left-hand side, that's the transformation I just showed you. There's a Chern-Simons theory at level 1. It has 2 maximal branches, and there's a duality onto a non-Chern-Simons theory, which we call Q, which has a Higgs and Coulomb branch, and we can just map them across the duality and do computations. Good. But there's another, for now, very innocent-looking transformation that you can do. You can take the T generator of SL2Z and apply it to the brane system. And what it will do is it will swap the NS and the 1,1. What it will also do on the Chern-Simons side, it will basically swap the 2 maximal branches. Because if you swap NS and 1,1, you do swap the maximal branches, right? So you sort of have this feature here, but we know a feature that swaps maximal branches in the non-Chern-Simons theory, that's basically the S duality. Right, so you can complete the figure by having this nice commutative diagram, and then you can compute the A and B branches by whatever Higgs Coulomb branch you want. Okay. You might say that was not very exciting because it's Chern-Simons level being 1, right? But it becomes more exciting if you go to Chern-Simons level greater 1, because then you don't have this luxury of an SL2Z duality anymore that takes you to a non-Chern-Simons theory. So now you really are stuck with the Chern-Simons setup, and you need to learn how to deal with it. So take a simple example. That is, we have 3 NS5 branes. We have these 1, kappa branes. So you would get a Chern-Simons matter quiver, which has 4 gauge nodes. They have alternating Chern-Simons level kappa plus minus kappa. They have bifundamental matter fields, and then that's life. Okay. Now what we want to do is we want to start reading off a magnetic quiver for each maximal branch. So let's start with the NS branch. So that will be the red branch here, and we will want to move these NS branes between the NS5 branes. So how do we do this? We say, okay, since we know what the moduli are, the 3 moving between NS, we assign to the number of them a gauge node in the magnetic quiver, right? So here I have N, and this N corresponds to the number of the 3 segments that I can move independently between the 2 NS5 branes on the left. Same here, I have two NS5 branes, which in between I can move at most N. So I have another one here. So I've taken care of the NS branes. Now I only need to take care of the 1, kappa branes. And those, the proposal is they give you just flavor, right? So that's what they would do. In this interval, they would contribute kappa flavors, here as well, kappa flavors. Okay. Now, what can we do? We can do the 0-order exercise. We can count dimensions. But dimension counting is very, very easy because here you see there's N. Here you see there's another N. If this is the magnetic quiver, we would just need to compute the dimension of the Coulomb branch, but it's just the sum of the ranks, so it's also 2N. Okay, that was by construction, a correct answer. But can we actually check more? The answer is yes. You can compute the superconformal index of the Chern-Simons theory. You can refine it, and then you take the limit to the maximal branch A or B by the work of Shlomo. And then you get the Hilbert series of the maximal branch, and you can compare it to the Hilbert series you would get from the magnetic quiver, and you find they agree, right? So very nice. That is, we're not doing anything wrong. And you now, with this sort of approach, you can sort of generalize most of the observations that have been done on the maximal branch in 3D Anchors 4 Chern-Simons matter theories that have been in the literature before, where sort of people have looked at the index. So in this particular limit, the index behaves as the Hilbert series of this and this particular quiver, right? So now this is a very straightforward exercise. You take a brane system, you write down a magnetic quiver, and you're done. Yes, you have, so it's a 3D n equals 4 theory. So in the index, you have the two fugacities for the R symmetry and the axial symmetry. And you just take a combination thereof which projects onto the maximal, basically the Higgs and Coulomb bunch of the 3D n equals 4 theory.
But for project time.
No, so it's a 3D n equals 4 theory. So this one, yes. Right, so you compute the index with the n equals 2 R symmetry and the axial U1 symmetry. And then you can take a combination of them, call them x and t, and you take the combinations. And if you then take one of the combinations to 0, and then the other one is basically the Hilbert series fugacity on the A branch, whereas if you do the other limit, you get the Hilbert series fugacity on the B branch. Right? So, yeah, it's the usual one for non-Chern-Simons. But we only really know, we only really use that it's n equals 4 theory. So you need to be sure that what you do is correct and that you can actually turn on the axial symmetry. But once you're sure you can turn it on, then you can take the limit and see that you get basically the Hilbert series for the maximal branches. Right? Yeah, so in this sense, we're really just using that it's n equals 4. Good. Okay, so now what we have done so far is we have written down a recipe that works for the A branch, which is one of the two maximal branches. So now how do we do about the second branch? Well, here we don't really have to work anything anymore because we just remember there's a very cute transformation on the brane system which swaps your branes, right? You just take t to the appropriate power, you swap 1 kappa with an s. But now this is the dual brane system which has branches swapped. So now we can just apply the same recipe on this particular brane system, and the magnetic quiver you would get is the one for the B branch of the original one. All right. So if you do this, you read off a magnetic quiver like this, and you can do the computation, and you see it works out, and somehow this B branch magnetic quiver business has somehow not been shown up in the index computations of in the literature. So that was sort of not appreciated or found out. Don't know why, but now it's actually a very simple exercise. You just do a nice transformation in the brane system, and you're good to go. Right? So in this sense, you have now this very nice feature which sort of generalizes the kappa being 1 case, that you have the Chern-Simons theory, you read off the magnetic quiver straight away, and then you go to a dual one to read off the magnetic quiver of the second branch, and you're good to go. You compute both maximal branches with a nice Coulomb bunch problem. Okay. Now, for later purposes, there's one there's one feature that I want to emphasize a little bit. Because if you want to read off the magnetic quiver, you basically do the same exercise that you always do with brane systems. You need to care about brane creation and annihilation. So if I give you this Chern-Simons quiver here, and I tell you there's a number of D3 branes n and m, suppose one of it is bigger than the other, then I could write my brane system equivalently like this. I just split the branes. I say the number of moduli between the ns is m, the smaller one. And then I have a number of D3 branes which are sort of stuck between the ns and the 1 kappa. They are not contributing to the maximal branch simply because they cannot move between them. And then if you use brane creation annihilation, you can bring this one outside. Now this one is basically the way to read the magnetic quiver. You do a duality on the Chern-Simons matter theory. You use a brane creation annihilation, and then you read your maximal branch magnetic quiver just from this configuration, because those ones are the ones that contribute to the moduli, and these ones are basically the flavors. Right? So that's a nice way of doing it. And if you do a bigger example, you can use the same logic. You have these two number of D3 branes, and now you would say there's a number of D3s which are stuck between the 1 kappa and the m, and this then modifies how the 1 kappa contributes in each interval, because you could say there's kappa 5 charge here, but L of them are basically dragged into the next interval. Right? So that's how you use the standard brane creation now adapted to the 1 kappa 5 brane to read off the magnetic quiver. Great. That was the n equals 4 setup. But as I said, there's really no difference in terms of the brane system between having 2 different types of phi branes and having 15 different types of phi branes. It's the same kind of exercise. Right? So we can ask ourselves, can we do n equals 3 Chern-Simons matter theories, meaning we have more than one type of phi brane. And an example you can do, an abelian one, is you take an S branes, you take 5 D5 branes, and you take 1 kappa. Now, you do the same exercise. You read off the magnetic quiver from this one. You get some nice SQD. You go to the 1 kappa branch by the suitable T transformation, and you get another magnetic quiver. And for the D5 one, you just do an S duality, and you get another magnetic quiver. Now the question is, how much can we test? Since it's n equals 3, we cannot play the same game with the index anymore. Right? We can compute the index, but there's no limit onto a maximal branch. So that one goes out. But we were very fortunate, and that's also the reason why we chose this example to demonstrate, is that Benjamin Assel has been working on abelian n equals 3 vacua a while back. And he computed, from a brane system the chiral ring relations you should have on the Coulomb branch or on these maximal branches. Right? So if you look in the paper, there's a long derivation of some relations, and if you translate the relations into quivers, that's precisely what you find. Right? So in this sense, it's a nice consistency check that what we're doing is not completely out of the window. But there's also an important point in the way that Asa was deriving these quantum relations is a very tedious thing, and it's slightly very tedious to go to non-abelian things. Whereas here, it is not at all tedious to go to non-abelian. You just put more n D3 branes, and you use the same principle to read off the magnetic quiver.
So the relations are
the relations are what is the maximal branch, and then he wrote down what is the relation on the generator for this maximal branch. And now we translated them into the magnetic quiver, right? So
there is a long list.
oh, there's a long derivation.
Derivation.
Yes. Well, the final answer in this abelian example is very short. If you go to a longer abelian answer, example, the answer is very long because then many nodes talk to one another.
For this case,
well, it's just the standard one you would, yeah, right. But the derivation is very long. Whereas here, you do it in some minutes. Right. Sure. Right. So again, there's no reason not to go non-abelian. You can just do it, right? There's one more thing that we might appreciate if you see what I secretly did here. So I started with, I told you that I start with NS5, D5, 1 kappa, right? And then I said, okay, you can just do things very nicely. But then actually, if you do S duality here, you already secretly see that I encountered a kappa comma 1, a kappa comma minus 1, right? So from the brane system, again, there's no real reason that I should restrict myself to 1 kappa. There's no good reason to do so. And in fact, you can do the same with PQ5 branes, right? So again, there's not much of a difference. You take a PQ5 brane, you have this nice representation in terms of these continued fractions. And then for this system, it is already strongly coupled because we know there's some kind of a Quivers-like description, which has matter fields, which are basically SCFTs, right? So from this representation of these continued fractions, you get a number of Chern-Simons gauge nodes, and then the links in between are already SCFTs. So it's a possible description, but it's very cumbersome to work with. If you use the brane system, there's no real difference to the cases what we have done before. You just need to take the brane charges appropriately into account. So if you take an example that generalizes the 1 kappa to PQ, you read off the magnetic quiver. You go to the PQ branch. By the PQ branch, now we need to use a slightly more general SL2Z transformation that you can work out. And then the only thing that we need, according to the recipe, is the 5 brane charges, which turn out to be nicely P and Q. And you read off a magnetic quiver. And you do the same for the NS branch, and you read off a magnetic quiver. Do we have anything to check? Again, no index, but Assel was kind enough to provide us with an answer, which reassured us that what we're doing is correct, right? And again, you can do this non-abelian, so it works out. Why am I telling you all this in such excruciating detail? Because once you have taken the brane system and you derive a magnetic quiver, you can basically unleash all the magnetic quiver 3D-4 machinery that you have. You can compute Hilbert series, you can compute Hasse diagrams, right? So everything that you want to know about particular information about these maximal branches, you can just compute once you have the magnetic quiver. Okay. Yes.
Yeah, but what's the theory interpretation of the?
It's this one. So you say it's sort of a strongly coupled object, which has some quiver-like thing, which basically replaces some of the bifundamentals with an SCFT, right? So it's this TUN SCFT that you would put as a link, and then you would be able to compute something from this theory, right? Good. Okay. Now we had this. Okay. Now, once you have convinced yourself that a brane system with D5 and D3 works out nicely, you go to your student and tell them, what's nice, you could just generalize this by including O3 planes. That's so always a nice exercise, and that's something that we have tried with Fabio and Sinan. And it is actually a more intricate story than one may have expected at the beginning, but it turns out also to be very educational. So let's go through this in some detail. So what we do is we upgrade our setup by including O3 planes. If you allow yourself to do this, then what we know is that the gauge groups change now to SP and orthogonal type. Okay. If we do this, we also know that we need to adjust a few things. We need to, again, reconsider brane creation and annihilation because now we have the O3 plane. And basically, the basic brane moves are also represented by basic n=3 Chern-Simons dualities that has been studied in literature. So that's a nice feature that already some is done. And you encounter a problem that orthogonal nodes, you need to specify what's the global form, right? So are we talking about SO? Are we talking about O? Are we talking spin and pin? Those kind of questions now arise, similar to what Antoine has alluded to. And the strategy, however, to read off the magnetic quiver is very similar. It's basically you take your brane system, you use the brane creation and annihilation transformations to bring it in a suitable phase where you then want to read off a magnetic quiver. And that is very similar to what you do in standard mirror symmetry with O3s or the same magnetic quiver derivations for 6- and 5-dimensional orthosymplectic magnetic quivers. So it's, in principle, a very straightforward task how to do it. So let's do an example. You take, again, a 2-node Chern-Simons meta theory with orthogonal and symplectic. And when I write SO here, then I'm pretty ignorant about what's the global form for now. Right? I just write down what it is. And then we use brane creation and annihilation. So if my left interval is bigger than the right one, then I know that the number of moduli that contribute to the branch between the NS is M, right? So the smaller number of D3 branes, that one I can consistently move along the NS5 branes. So that one is a good number. And then I move the 1,2 kappa to the other side. I get some brane creation annihilation, and I get to begin with, first of all, a dual brane system that describes now some dual Chern-Simons matter theory. But from this Chern-Simons matter theory, we now propose that we can read off the magnetic quiver just by focusing on what happens between the NS branes. Right? So the NS branes here are, and I realize I haven't explained this, there's a reason why there is dotted and dotted and nothing lines. These are basically what represents the orientifolds. So here the dotted line is an SP, is a plus orientifold. This one is a minus orientifold. That's why I get orthogonal. This one is plus, and this one is minus again. So that's why we have SP here. So if we go to this phase of the brane system, we see there's MD3 on top of an O3 plus. So this one gives us a symplectic type gauge node in the magnetic quiver. And then again, how do I read off the flavors? Just by the number of D3 branes which are not on the moduli or not on the maximal branch. Okay, can do this. So that's a promising start. Then what happens if the other number, so n is smaller than m? Well, then I could go to the other direction. I repeat the exercise. I do a brane transition. And now I have a very clear orientifold 3-plane between the NS branes, which is minus. So I would read off an orthogonal gauge node and some number of flavors, which we can't really see right now, but it's basically this number here. Okay, good. So now we have this, and you see there is already some subtle, well, there's some nice feature. Now check what happens if n is equal to m. If n is equal to m, I could in principle do both. And then I would expect that, well, anyone reasonably thinking about magnetic quivers should suspect that the two magnetic quivers should give you the same. But this is already where things get interesting, and that you should refine your computations a bit more carefully, because we know that this SP SQCD Coulomb branch is the same as this orthogonal SQCD Coulomb branch, only if we take the orthogonal global form. Right, so there's already an indication that we need to be a bit more careful than just thinking about the algebras. So let's let's take this in a step further and do a bigger example. Now we allow ourselves to have a different type of oriental just to keep it interesting. So now this line here is a minus tilde. This is a plus tilde, minus tilde, plus tilde, minus tilde. So in turn, we get an symplectic node and we get an orthogonal node with an odd number. Okay. Now in this brane system again, what do I want to do? I want to read over magnetic quiver for the NS branch, right? So the one between the two red lines. And for this, again, I can use brane transitions. I get into something that looks like this. And here, very clearly, I have an minus tilde orientifold. So I get an SO odd type gauge quantum magnetic quiver. And if I have them both to be equal, I can also go to this brane trace where I get an SP. Right? And what I observe again is, first of all, that the magnetic quiver for this A branch depends on all three numbers that I put into the game, m, n, and kappa. And if n is equal to m, I again have the question, do my magnetic quivers give me the same answer? If we go to the B branch of this exercise, then what I would do is the same logic as in the unitary case. I would apply a suitable S to Z duality, which swaps my 5 branes. And then I would read off again between the NS branes. So here I would get an SO type node, or I would get an SP type magnetic quiver depending on how I move my branes. Okay. What I observe is very happily that my B branch is only dependent on m and n, but not on kappa. Right, this is a nice consistency check because if you remember the original brane system, basically what does it mean to be a B branch modulus? It just means I can move along the 1,2 kappa. Right, moving along this, if the m and n satisfy a nice relation, which I need for this quiver to be good, means just my m and m can just move unconstrained, and I don't really see the Chern-Simons level. I just see the number of flavors on the side. So that's a very nice consistency with the derivation. But again, I run into the question: are the SO and SP type magnetic quivers the same? So once we encounter this feature that you have two different magnetic quivers for the same branch. At the beginning, I was very happy because we know of some cases where an SO and SP give you the same answer. But then you also had the question, how do you do this in a bigger quiver? How does it relate to the global forms? So we took a step back and asked ourselves, what do we know from the brane system? So we know, of course, the maximal branch dimensions, but that's sort of built in by definition that this is correct. We can get the global symmetries on the maximal branch for SO type for sure, for SP type, not really, but so let's say, okay, almost. Can I get the Hasse diagram and the Higgsing? If I use the branes, I can more or less get it, but it's not a complete algorithm yet. But most importantly, one of the basic features that we use to do computations, the Hilbert series, we cannot get yet unless we specify what is precisely the global form that we put in, right? And in the previous autosymplectic magnetic quiver constructions in 6 dimensions, 5 dimensions, we were sort of very lucky that we got away with the answer. It's basically SO everywhere, and then there's some diagonal Z2 that we need to take into account. Here the answer turns out to be a bit more involved. So we just remind ourselves that if we have the SO, we have the magnetic symmetry, and we have the charge conjugation chirality symmetry, which then give us the opportunity to go to the different global forms. And we know very happily that these play a role if we do basic brane moves, right? Basic brane moves translate into basic Chern-Simons matter dualities. So we know, for instance, if we take an SO SQCD type theory and we do the basic duality, we get, again, an SO type Chern-Simons matter theory with some different rank. We get some a priori different fugacities for these discrete symmetries. And we need to make sure that we map them correctly, right? So that's something that turns out to be now very crucial if you want to do the statements a bit more correct. So how does this work? The idea is the following. We start from a brane system that we want to understand. And then we use the brane creation annihilation brane moves to go into a phase where we would say this is a nice phase to read over magnetic quiver. Right, so this is a nice phase because now I have between my NS branes, I have a very clear O3 orientifold, so I know what to read. I have some, let's say, branes that are not on the same branch anymore, so I can put them as a flavor. And now I would be tempted to read a magnetic quiver from this phase, right? So what I would to do is I would say this is an SO type node, and I would say, okay, it comes from here. So I would identify the fugacities that I can put into the magnetic quiver with the fugacities that I would put onto this dual Chern-Simons matter theory. Okay. Then the next step that I would need to do is I would need to trace back where do these, or how do these fugacities relate to the original Chern-Simons matter theory. That's where this basic Chern-Simons dualities come into the game. And then I need to sit down and do the computation, and I find if I do it, I get a map like this. All right, so what do I see? Well, so we have an original, this is the Chern-Simons matter theory that I want and to understand the maximal branch. And then I have this object, and this magnetic quiver now tells me, okay, I should redefine my fugacities like this, and then I at least get a matching with the index and the Hibbetsius limit. But we also see that, of course, the magnetic quiver is only a subset of the information that I have from the Chern-Simons matter theory. For instance, the zeta 2 that comes in here is not really represented in this magnetic quiver here, which is also fine, right? So it just means that on the maximal branch that belongs to the NS branes, I don't have any dependence on zeta 2. And that's a fair statement, and to be expected since the magnetic quiver is only sensitive to some information of the theory. And again, you can test this prescription by doing some index and Hibbetsius computations. And so that's one way of testing this. And it took us a while to figure out that, well, there were several steps of evolution in things, right? The first step was you take a brane system, you have orientifulls, you do brane moves, and you read off a magnetic quiver, and you have gauge algebras. And then very happy. But then you try to do, or you have the luxury of doing computations on a Chern-Simons matter side, so you can actually ask how much does it match, and does it match like with any global form? And then you find out, okay, it doesn't really match obviously, so we needed to figure out how these dualities work out. And once you have it, you get some very interesting results, because now if you take a more general example, you find, yeah, to me, slightly puzzling results in a sense. The prescription is the same. You do brane moves, and then you get one or several magnetic quivers for the same Chern-Simons matter theory, the same branch. But then in order to make the computations match, you really need to take care of the sequence of Chern-Simons dualities that you have done on the brane system to go to that brane phase. And then you would say, for instance, in this example, you have 6 nodes in the Chern-Simons matter quiver, so you have 3 sets of fugacities. You can go to a brane phase where you read off a magnetic quiver that is SO, SP, SO. And then you would need to match the fugacities in a manner that is written here. But you can also go to a brane phase where you read off a magnetic quiver that is SP, SO, SP. And then you find a different fugacity map. Right? So I'm happy with the understanding that not all of the fugacities are transparent in all of the magnetic quivers, because I'm expecting only some sets of information being represented by the maximal branch. But these subtle fugacity mappings came to a surprise that was unexpected when we started. That's, yeah.
There's something that you're trying to kind of guess, which is this characterization. So mappable, you can follow to
Yes.
step.
Yes, you can follow, right? So very good, right? So you go to the next office, you go to Nopodol, and he would tell you this is the one you should do. So you go to your brane system, and then you ask the question, do I do a duality on SO, or do I do a duality on SP? If you do a duality on SO, you use, I'm going to say Nopodol's map, but basically that, and then you relate the ones in between. If you do SP, it took us a while to figure out that there's also something going on. And that something going on depends on whether you have 1 or 2 SO nodes connected to it. And then you have a different type of duality map for an SP brane move. Right? And then you can basically sequentially combine all of these moves. You have your original brane system, you go to a brane system where you read off your magnetic quiver, and then you just need to trace back all of the fugacities.
Follow through and
well, I mean, computationally, there's no puzzle. Conceptually, I was not expecting this. Right? So because, I mean, so you have 2 different sets of magnetic quivers. I mean, you have 2 different looking magnetic quivers. If you're very ignorant about the global forms, you could say they behave very nicely. And if I do the standard example of SO, or let's say of orthogonal SQCD and SP SQCD, which have the same Coulomb bunch, this works out nicely. But if you start asking more refined questions like turning on fugacities, then you get this kind of funny looking maps, which you need to take into account. Do I have an explanation of how this and this both map together and how they interplay? Not really yet. Right? So it's for now, it's really you sit down, you have a brane system, you follow the brane moves, and you get fugacity maps. Yeah, that's the thing that's confusing, because also you can so there is, for instance, in 3D mirror symmetry, or in some of the works that Napadol has been recently doing, the question, what is the precise choice of the orthogonal gauge groups in 3D mirror symmetry? And the answer is sort of more convoluted, confusing than expected. And yeah, here we are in the luxury that we can actually do computations so that we get an honest map. But the map is not yet contributing more to my understanding than I would have hoped. Right? But it's a map that you can compute and you can check. Okay, what do I want to conclude with? Well, the conclusion is twofold. If you can afford, stay unitary. That's a very nice way of doing computations, because here we have less difficulties. We have a very nice way magnetic quivers capture the quantum branches. We have decay fission working very nicely, and your life is very satisfying. If you want to explore autosymplectic ones, be aware a lot of things are more complicated than you may have initially guessed. We can still get magnetic quivers from brane system. That's a nice way of doing it. We do get the feature now that we have multiple orthogonal or orthosymplectic magnetic quivers for the same branch. So that's kind of a new feature. And they sort of depend very intricately on the global forms that you would put in. And that, again, is a feature that also Nopadol and Ami and Sam have been discussing recently. So the question is not an answered one yet. If you ask the same question about the Higgsing pattern, like in the unitary case, I argued that you can basically use decay fission to go along the Coulomb branch or G-flows of the quiver. Well, for autosymplectic, again, it's more like a construction site than a fully developed story. There is some version of decay fission that has been promoted and has been put forward, but it's not yet the final answer. In the cases that we know for the Chern-Simons matter theories with the O3s, we know that the quivers that we're getting are basically linear autosymplectic quivers. So that's the T rho sigma cases that we know. So here in principle, there's no difficulty. It's just cumbersome to work out. And there's some subtleties that you need to take into account. The future directions, of course, is there's so much you can do with brane systems. I mean, there's some extensions you can consider our indifferent phi branes, but there's also, of course, Chern-Simons matter theories which are beyond brane systems. And for them, it would be a long-term dream to work them out in the same rigor with magnetic quivers. So that's a thing that we want to include at some point. And you also know that, for instance, in the Chern-Simons matter theories that I showed, like SO even SP, we know there's a one-form symmetry that we haven't really touched yet. In the examples, we always left it there. We haven't gauged it yet. If we would have gauged it, we would get another zero-form symmetry. And then you can ask the same question. What can we do about this symmetry mapping, and what are the magnetic quivers that we would get? Things that I haven't covered yet, and which I just wanted to raise, is that, again, this problem with the magnetic quivers from your favorite singularity. And of course, the classifications that we have been doing that are sort of essential for the decay fission process. So that's the work with Antoine, Quentin, and Sinan. And with this, I would like to thank you very much for the attention.
For the really simple, I didn't quite get what is the conceptually surprising part of having different for the same branch. I got so like, for example, in the paper the machine people in 5D where we find the example of renormalization the same theory, one we don't get from the out.
Oh, yes.
Exactly the same. I mean, two different.
Yes. Yes.
Providing another level of accidental one.
Right. Very good, right? So, okay. Tell me if I misunderstood you. So there are some theories which I can realize with or without orientifold, and then I would get a unitary or autosymplectic magnetic quiver. Very good. This is what I'm very happy with, because then I have basically two different constructions, and I would get two different magnetic quivers which have the same Coulomb bunch. Very good. For the autosymplectic magnetic quivers that I was used to, there was never the trouble of like having two different magnetic quivers from the same brane system. Because there was sort of a very canonical canonical phase of the brane system where I should go to read off the magnetic quiver, because we were dealing with an SCFT, so all the NS branes basically had to go together. Here, I have the freedom where to put my 1,2 kappa, and then depending on where I put it, I get a different magnetic quiver. They have unrefined at least the same Coulomb bunch geometries if I choose the gauge groups to be orthogonal. But then once I start putting in the fugacities and try to really understand what is going on from the Chern-Simons matter side, I get that they are sensitive to different combinations. And that was the thing I was not expecting, have seen before. You frame it the way you want. Yeah, I was just confused. But I mean, the way, let's put it differently. The fact that the magnetic quiver is not sensitive to all of the fugacities, I'm perfectly happy with, right? So that's fine. But that they show up in this particular combinations, yeah, something to explore further, I would say. Right, so it's really the same brane system, and I get, because let's differently. Unitary, you put your 1 kappa wherever you want, you still read off the same magnetic quiver because it's unitary. Here you have the orientifold magic going on, so whenever you move them differently, you get a change from SO to SP. And that's the thing that is just confusing to me. But the answer is correct, right? I mean, you have the same Coulomb bunch, but potentially not the same Higgs bunch. I mean, most likely not the same Higgs bunch, because you already see you have different global symmetries on the Higgs bunch.
But I have a question. Can you explain how you deduce the magnetic quivers from the brane system in general?
It depends which brane system and.
Well, you deduce it in general. You set up some brane system, which is the original theory.
Yes, this one.
So it's not the brane system for which the magnetic quiver is not the quiver describing brane system itself. It's an auxiliary.
Yes.
So if Amihai were absent, I would channel my best impression of him, and I would say that the proper way is not to relate to some 3D theory, but to find the appropriate replacement of the F1 string, so to find the appropriate probing objects for which the fundamental theory would be the magnetic quiver. What's up with that? So what's the status of that philosophy?
Let's take a slightly down-to-earth example, right? So take this Chern-Simons matter theory. And then in that Chern-Simons matter theory, you ask yourself, which monopole operators contribute to the NS5 branch? So which are the monopole operators that correspond to the D3 moduli that you can move along the NS5 branes?
You're already thinking D3s.
Yeah, because it's D3s here, right? So I
sorry if you were.
Yes.
Sorry.
No worries.
Jumped. You were not doing 3D. I mean, yeah, now you're studying 3D. When you're studying your 4 or 5 instead.
Yes.
In that case, you're not directly in the Hananic framework. You have some brane system.
Yes. Oh, very good. Right. Okay.
Right.
So if you.
Yeah. So it really relates more to the first third.
Oh, I see. Okay. No worries. I mean, so if you have this one, right? And then so the different phases of the same brane system, right? So if you would have NS5 between sorry, I shouldn't say this. DP between NS5. Right, so this is what you usually would call the Coulomb branch phase, or let's say the electric phase, or that's where everybody would write down the quiver for the theory that you study. But then in the brane system how the Higgs bunch is realized, because it's the Higgs bunch that we want, right? So and for this one, what you need to do is you need to move. So let's say you do Hanani-Witten moves to a configuration where the dp are between dp plus 2, right? And this in all of the brane systems from 3 to 6 dimensions, that's the brane system phase of the Higgs bunch, right? Because you know that sort of the rotation symmetries acting on this bunch is an SU2. That's the Higgs bunch hyper-Kähler rotations. So that's the phase of the brane system where you would start reading off the magnetic quiver. You would say if you have something like this, right, and then you have n dp between these dp plus 2, they're free to move, then that's n magnetic moduli that you would turn on. Then the usual question is how you deal with this ns. And that depends a bit on the dimensions. If in 6 dimensions, then there's a way of adding them as gauge groups. If you're in 5 dimensions, you rather think about the 5 brane webs and how the web is moving as a moduli. But the logic is always the same. You go to the Higgs bunch phase of the brane system, which is Hanani-Witten into dp to between dp plus 2. And that's the same what we do here, right? So now generalize what is your maximal branch. Now the maximal branch is not dp between dp plus 2, but it's d3 between some 5 brane type, right? So now is d3, sorry, between some pq5 brane. Then you apply the same logic. Now you replace the vertical lines with slightly slanted lines because it's pq5 branes, and then you say it's still moduli. And then the question remains again, now what I do with the other 5 branes. And in order to deal with the other 5 branes, I use now the Chern-Simons equivalent of these brane moves to move them somewhere where I can clearly read off branes between the pq5 branes and branes which are between 2 different types of 5 branes. They are not moduli anymore, so I take them as flavors.
So the real conceptually difficult case is NS5s in other dimensions. How to throw it in as extra nodes.
Well, conceptually, you say there's a Higgs bunch phase, dp between dp plus 2, and then figure out what happens with the rest of the branes, because that's sort of the same exercise here, right? You say d3 between one type of 5 branes, and then you just need to figure out how do the other 5 branes affect the moduli that move between these pq5 branes, and that depends a bit on where you are, right? But the story is always let's say they're beautiful and conceptually satisfying because it's the same brane moves you do in every dimensions. You just need to be careful with charge conservation and things. So you happy with this?
Yeah, well, we can discuss more.
Okay.
Here, but I was thinking 6 dimensions where the NS5 by itself already gets represented as a node. That's not immediately, that requires some.
Yes. I mean,
I was wondering whether I say that, if you find the appropriate fundamental probing object, that you will always get you should get the answer. First principles and not by guessing.
In principle, I guess. I mean, that would okay. So in the first 16 magnetic quivers, there was no intervals. You just said in 3 dimensions it's d1 string that you would read off, or that you would use to read off the magnetic quiver for the Higgs bunch phase. Then you go up, it would be a d4. Right, so now you would need to work out how they suspend, but in principle it should be the same as the Thiel version down. And then, well, d4 between NS5, that's an extra piece of recipe. Right. But I mean, so one naive answer is at least the NS5 in 6 dimensions has the same sort of word volume as the 6-dimensional theory itself. So if you have the NS5 branes, it's suggestive to add it as a modulus, not as a flavor. Okay.
Never find a case in which there are different magnetic quivers and one is good and one is bad in the sense of
Okay, so good question. So we have used magnetic quivers to sort of constrain the Chern-Simons theory whether it's good or not, right? Because that's sometimes not very obvious. And then by this logic, we have not found it because we basically said you have the magnetic quivers, you check what are the conditions for them to be good, and you impose the strongest one on the entire theory to have everything well defined. You can have theories where one branch is good and the other branch is bad. I mean, there's a very simple example here. Is that the example that I want? Yes, yeah, that's the example that I want. So what is this? Here, right? Look at this. Very beautiful. So there's a Chern-Simons node here, there's a Chern-Simons node here, and then this is actually an X4 node, right? So here, standard goodness applies. So if your n is smaller than m, you can still work out the NS5 branch, and you get a quiver that is sufficiently good if you pimp up kappa. But the B branch is always bad. But the explanation is very simple, right? Because the B branch by itself already was something that we understood without doing Chern-Simons. Right? But then you would say that the whole Chern-Simons theory is not good. Good.
Not then, thank Marcus again.